Advanced Math Set 107, Convergent Geometric Series. Okay, so we've done geometric series in the last couple of lessons, and we are just going to go over one more time how to find the formula for the sum of a geometric series. So if you remember, you have to multiply by negative r so that you can get all of the middle terms to drop out, and then you add the sum and the negative r times the sum to find that you end up with a sub 1, everything else cancels out, minus a sub 1 times r to the nth power. Now on the left hand side you take out an s sub n, and on the right hand side you can pull out an a sub 1, and then finally divide both sides by 1 minus r. So we find that the sum of a geometric series is a sub 1 times 1 minus r to the nth power all over 1 minus r. So if r sub n is very small, then we can figure out that 1 minus r sub n is almost always going to equal 1. So think about making r sub n a very, very, very small number, and as it's a very, very small number, then 1 minus that number is always going to be very close to 1. So for example, we'll let r sub n equal 0.000001. So the sum of n is going to be a sub 1 times 1 minus 0.000001 all over 1 minus r. So we get 0.9999999, which is very close to 1. So as r sub n gets smaller and smaller, 1 minus r sub n gets closer and closer to 1. We're going to accept that as good enough, so we can say that 1 minus r sub n approaches 1 as a limit as r sub n gets smaller. So limit is a new term. It's a term that's used a lot in calculus, and it's basically what the sum approaches as the numbers continue on in the series. So basically, for this to be true, for it to be equal to 1, we need r to be between negative 1 and 0 and between 0 and 1. So basically it needs to be a fraction or a decimal, negative or positive. So as n increases, r sub n is going to get very, very small. So for example, if we let r equal 1/2, then r is in between our parameters. It's in between 0 and 1. And we'll say that we'll let n equal 12. So if we have 1/2 to the 12th power, that's the same as 1 over 4096, which gives us a decimal number of 0.00024441, which is very close to 0. So if we do 1 minus r sub n, we find that we get 0.9997559, which is very close to 1. So we are going to assume that if our value of r is in between 0 and 1, or 0 and negative 1, that we will let 1 minus r sub n just equal 1. So our new equation for the sum of a geometric series is going to drop out that 1 minus r sub n and just make it equal to 1, so we end up with a sub 1 over 1 minus r. Now this is true, again, for those two parameters. So we say the absolute value of r has to be less than 1, and that's called a convergent geometric series. It's getting smaller and smaller as the series goes on. Now, if it's not less than 1, if the absolute value of r is greater than 1, it's called a it's called a divergent series. And a divergent series gets bigger and bigger, and so you can't find the sum of a divergent series. You can only find the sum of a convergent series. So we'll do some examples about finding the sums of convergent series. So find the sum of this infinite geometric series. So we have 5 plus 5 halves plus 5 fourths plus 5 eighths, and so on. So our a sub 1 is 5. Our r is 1/2, because you notice each term, if we multiply 5 times 1/2, we get 5 halves. If we multiply 5 halves times 1/2, we get 5 fourths, and so on. So the absolute value of r is less than 1, so we know that we have a convergent series. So we can use our formula, s equals a sub 1 over 1 minus r. So s equals 5 over 1 minus 1 half. S is equal to 5 over 1 half, which is equal to 10. So we know that if we add this series together and we go on forever and ever, that this series is going to approach 10. It gets closer and closer to 10 as the series goes on. So the interesting thing is that it's never going to get bigger than 10. No matter how long you add this series, you can keep going infinitely, and this will never get bigger than 10. It will always just approach 10. So we'll do another example. A ball is dropped from a height of 12 feet. It rebounds 2/5 of the fall distance on each succeeding bounce. How far will the ball fall on the 10th fall, and what will be the total distance the ball will travel? So we'll draw a picture of what this is going to look like. We start with 12 feet, and then the ball is going to bounce, and then it's going to come up just 2/5 of the distance. My drawing is not accurate by that standpoint, but you kind of get the picture. It gets smaller and smaller as the ball bounces. Now we are assuming that the ball is bouncing kind of in the same line. I just have it stretched out so that you can kind of see what's going on. And that'll come into play with this part B of our problem. But what we do know is that our series is going to look like this. It's going to start with 12. Then the next bounce will be 2/5 of 12. The next bounce will be 2/5 squared times 12. Then 2/5 to the third power of 12, and so on, until we get to the n minus 1 power of 2/5 times 12. So we needed to find the 10th fall, so how far the ball has fallen on the 10th fall. So we just use 12 times 2/5 to the 9th power, and we find that it's 12 times 0.0002621, which is equal to 0.0031452 feet. So very, very small bounce. Now we need to move on and see the total distance the ball will travel. So this one we have to be a little bit careful with, because we'll be able to find the sum of the distance that it falls, but that's only going to give us half of our answer. So we know that our initial value is 12. We know that the ratio, or the R value, is going to be 2/5 because it falls 2/5 of every one. And 2/5 is less than 1, so we know this is a convergent series. So we can use our formula, S equals a sub 1 over 1 minus R. A sub 1 is 12, and 1 minus 2/5 goes on the bottom, so we get 12 over 3/5, which is the same thing as 60 over 3, or 20. But again, I said this is only when the ball is dropping, and you can look back at the picture, it's only the red part of it. Now we need to figure out the up part, so we need to figure out the yellow. The only thing, it's going to be exactly the same as the falling, except that it doesn't include that initial 12 feet. So in order to take out that initial 12 feet, we're going to take our 20 that we just got, and we're going to subtract that initial 12 from the value of 20, which is the sum of all of the downs. So 20 minus 12 gives us 8. So then all we have to do is take the ups and add them to the downs, so we get 28 feet. Okay, last example. A rabbit runs 2 miles in the first minute, 0.8 miles in the next minute, 0.32 miles in the next minute, and 0.4 times this distance in the next minute. How far will the rabbit travel in all if he continues this process indefinitely? So this problem is a little bit quirky. I'm not sure that the rabbit can actually run 2 miles in 1 minute, but we'll just take the problem as it is. And it says he's going to run indefinitely, which, again, not very probable. But it does tell us that he's running 0.4 times the distance in the next minute, so we can assume that our R is 0.4, but we want to double check it. So we're going to take 2 and times it by 0.4, and we do get the next value, which is 0.8. And when we multiply 0.8 times 0.4, we get 0.32. So that checks out that our r is going to be 0.4. So our initial value is going to be 2, and our r is going to be 0.4. 0.4 is less than 1, so it does check out as a convergent series. So a sub 1 is 2, and r is 0.4, so we have 2 over 1 minus 0.4, or 2 over 0.6. 0.6 is 3/5. 2 divided by 3/5 is 10/3. So the rabbit is going to run 10/3 miles total, or in other words, 3 1/3 miles, if this were even probable.